Welcome. Just a quick video I'm going to put together just to cover the energy systems. I'm going to be nice and quick just because I don't know quite how good my internet system is going to be over here. But last video I looked at the ATP PC system. We talked about the body's energy currency. And so today we're going to look at the remaining two energy systems. So without further ado, let me crack on. So again, just remembering, we're working to describe, explain, analyze the three energy systems just near me who are just about to do some photography, so I'm going to be nice and quick. So we looked last time at this concept of the ATP breaking off a phosphate, releasing energy, and we talked about how that energy gets transferred onto a muscle fiber or any area in a cell that requires it. We looked at the phosphocreatine system as something that's going to be donating a phosphate and some associated energy to create a whole new ATP. And we kind of looked at this initial picture, and what we see is that we've got that very quick ATP PC system. So wherever we need these really quick bursts of energy, that's the system that provides that sort of kind of sharp maximal intensity energy for about a maximum of 10 to 15 seconds. So that system could even be used sort of within something like a football match where you've been playing for maybe a while, but you still need that quick burst of energy. So we're going to look at the other two systems. So this picture, I think the important thing to show is that actually the system kind of works side by side, so they kind of work in conjunction with each other. So it's not like we use the ATP system, ATP PT system, then the glycolysis system, and then the oxidative system. They're always kind of functioning at different stages to help each other out. So I'm going to start that section right now. So from last time, you should be able to look at these questions and figure out the answers, where to turn to figure out those answers. So have a quick look, just pause the presentation. So our ATP stores last about 10 to 15 seconds. We've got three energy systems. Oh, sorry, the number one should have read about 3 seconds. That's how long our ATP stores last. We've got three energy systems. The ATP PT system lasts about 10, maybe slightly longer seconds at maximal intensity. It uses phosphocreatine. And then really, once it's been used, we need our other energy systems to help restore it. So our aerobic system is really important to restore it. So if you've ever looked at, you look at an interview of Usain Bolt immediately after a 100-meter race, he's exhausted. His breathing is working very hard, but he's only done less than 10 seconds of exercise. So that extra oxygen has to be being used for something. So within the muscle cell, we have another energy system called our lactic acid system. Now you must have heard of lactic acid. Lactic acid is created in our muscles when we do intense exercise. And it's the sort of thing that makes our muscles feel like they're burning, but we always associate it with a much higher intensity of exercise than simply walking or very gentle jogging. So the picture I've got here kind of describes that process. We start with either glucose or glycogen. Glycogen is the body's way of storing. So it's a very long molecule of carbohydrate, basically. And I'm just going to trace it through. I'm going to draw a little picture on here to show here we're starting with glucose. So I've just got a little plus there. So we start with glucose or glycogen. What you'll see on this left-hand side, I'm just going to put a sort of 1 as I talk through the stages. So here's my stage 1. So stage 1 shows 2 molecules of ATP being used. So this is to break down glucose. Now, if I've started with glycogen, body's preferred way of storing glucose, I only use 1 molecule of ATP to start breaking it down. So whatever the start point, I'm already sort of down in terms of net ATP. What you see here is number 2. Hooray! I've created 4 molecules of ATP. So what's my net gain if I started with glucose? And what's my net gain if I started with glycogen? So what you should see is if I started with glucose, my net gain is 2. If I started with glycogen, my net gain is 3. Now, regardless of that start point, that breaking down of glucose leaves me with this substance called pyruvic acid. So pyruvic acid is on its own not a bad thing. It's down, any acid has potential to lose hydrogen ions. It raises or increases the amount of acidity in the body by losing these hydrogen molecules. In the absence of oxygen, i.e. if there's not enough oxygen, this happens at number 4. That pyruvic acid turns into lactic acid, builds up in the muscles, loses hydrogen ions and creates pain and stops the breakdown of additional glucose. So it leads to our fatigue. Hence why we call this system our lactic acid system. It creates lactic acid as a byproduct of breaking down glucose. And that's pretty much it. The important thing to note, and I'm just going to put a little 5 next to it, is that if there is enough oxygen, that lactic acid gets turned back into pyruvic acid. And that pyruvic acid can get taken in further and ultimately gets fed into the next energy system, which of course is going to be the aerobic energy system. So I've summarized the process here. I'm going to just read through it, but the thing I want to draw your attention to first is this table on the left hand side. Now, can you see where I mentioned glycogen earlier as the body's third energy for glucose? We've got around 500 grams of muscle glycogen. We've got about 110 grams of liver glycogen. The liver glycogen is very much used for our brain. The muscle glycogen is used in our muscles. It doesn't give us vast amounts of energy. If you look here, muscle glycogen, so this is shared across our whole body, gives around 2,000 calories. Now that's quite a lot really, but it shows it is relatively limited. So the lactic acid system is a means of providing quick energy to the body. It can be used maximally for around 1.5 minutes, or can be used to contribute smaller amounts for longer periods. So essentially what's saying is you can use your aerobic system in, say, a run, but as you increase that intensity, you might start using a little bit of your lactic acid. So it's not all out, it's just when intensity raises. Number 3, the fuel is glucose or glycogen, and you remember the difference between those start points. The waste product is lactic acid, which makes muscles hurt and interferes with muscle contraction and fuel breakdown. The system is used in any activity where intensity is high enough for the aerobic system not to be able to cover all the body's energy needs. Think of it a bit like a turbo on a car. So imagine you're walking along, start breaking into a very slow jog. You're still mainly aerobic. But then if you actually gradually, steadily start increasing your pace, your aerobic system won't be able to match that pace. So you'll start to use a little bit of your turbo. So your lactic acid system just starts to kick in. It doesn't have to be used all out, but it just starts to kick in. And the more you increase that intensity, the more you start to use of your lactic acid system. An example of a lactic acid system is in use could be when a fullback running down the wing to put a cross in, then has to sprint back to position. The intensity is high and longer than 20 seconds or so. So the lactic acid system is used. You'll then, when you stop, you'll show you've used one of your anaerobic energy systems by your breathing rate remaining very high. So the summary questions: what is the fuel used by the lactic acid system? How long can it provide energy for at maximal intensity? I want you to name an event that will maximally tax that system, and what the waste product is, why it is formed, and what is the name given to the breakdown of glucose or glycogen without the presence of oxygen. So pause your presentation now. So what you should have found: the fuel, glucose or glycogen, it can provide around 1.5 minutes of maximal intensity exercise. An event that will maximally tax it might be something like the 800 meters or 400 meters, but the waste product is lactic acid, and it forms because there's not enough oxygen present. The name given to the breakdown of glucose or glycogen without the presence of oxygen is anaerobic glycolysis. So we finally move on to the aerobic energy system. The aerobic energy system, what we've got on that picture on the right hand side, shows, if we see intensity change. So what we've got, I'll just draw a little pic. Do you see, as that intensity of exercise increases, so we move from, say, a walk onto a jog, onto a fast sprint, the type of fuel that we use is the relative percentage of it changes. So at rest, if I sort of put a 1 for rest here, that's good. So at rest, we're mostly using fats. So our fats are being broken down by our aerobic energy system. So our aerobic energy system is creating or is using fats and a tiny bit of carbohydrates. So as we increase that intensity, I'll put a 2 on there. As we increase the exercise intensity, we start to use more glucose. So our fats are still being used, but we reach our kind of maximal capacity for them to be broken down. So fats are very, very efficient, but they're not particularly quick way of breaking down energy. So as exercise intensity increases, the relative percentage of glucose being used begins to increase until we reach this point. I'll put it next to 3, where at very high intensity, the relative percentage of glucose we're using is at its maximum, and the amount of fats looks relatively low. So this is the relative percentage. So it means that the fats are still being used, but just at those high intensities, our body's ability to use glucose is much greater. So our aerobic system it takes place in the mitochondria. I'll draw a quick little mark on here to show. Can you see on that left hand side where mitochondria are? That's a picture of a muscle fiber, and within it are those little myofibrils, little rods of protein. So here I'm just going to outline mitochondria, and here is one in close up. So when we talk about the aerobic energy system, it takes place in these sections of within a muscle cell. And one of the things that changes as we get more aerobically fit is we actually start creating almost kind of bigger and more of these mitochondria. So we improve our aerobic energy system directly through this improvement in our mitochondria, or an increase in the number of mitochondria we have. So this is a kind of a summary of what's happening with aerobic glycolysis. So what we begin with, if we look at the top, I'll just do a little cross. What do you see happening here? Do you recognise that from anywhere? You should do, because it was one of the previous slides where we talked about the breakdown of glucose, the use of an ATP, the creation of an ATP, and the byproduct, I'll put a red mark next to it, being this pyruvate. So I've put on the right hand side, aerobic glycolysis starts with glucose or glycogen. At the end of glycolysis, pyruvate is produced. Now, I'm going to put a 1 next to that pyruvate. So pyruvate has been produced. Now, in this model, we move on to this stage here. So acetyl coenzyme A being created from that pyruvate. Now, if you remember the previous model, the pyruvate, in the absence of oxygen, turned into lactic acid. So here, that pyruvate becomes a substance called acetyl coenzyme A. Now, we don't need to know the whole sort of individual processes, but I'm just going to draw your attention to a couple of really important things. Now, what we can see, that acetyl coenzyme A, this stuff at number 2, gets fed into this thing called the Krebs cycle. Now, what we see on the Krebs cycle, we create a couple of molecules of ATP. You'll also see we create carbon dioxide. So the aerobic system continues that breakdown of glucose by just kind of washing it around another further system. Out of that system, we create carbon dioxide. Think about what we breathe out, carbon dioxide. We've also created another couple of molecules of ATP. Now, the important stuff that has been created, can you see hydrogen? Now think about what I said in the previous slides, was hydrogen on its own is sort of pretty bad for muscle. It creates acidity. Now here, hydrogen is kind of clipped onto these little carriers, and they take it to something called the electron transport chain. And here, the movement of these charged ions, these charged hydrogen ions, through the electron transport chain is used to create an energy that's used to reform or make loads of ATP. So I'm going to just outline it at the bottom there and put a 4 next to it. So the hydrogen from that Krebs cycle gets used to create an additional 28 molecules of ATP. So if we think about that net gain, if we started with glucose, we started with 2 at the end of that initial breakdown. We created another 2 after that Krebs cycle. But when we get to that electron transport chain, we create another 28 molecules of ATP. So you can see how much more efficient that aerobic energy system is. So this is a nice big complex diagram, and all I wanted to do with this was really show that in the aerobic energy system we can start with glycogen or glucose, but we can also start with fat, and we can also start with protein. And whatever the start point, we ultimately end up popping it in to that Krebs cycle. So they kind of end up there at different points. So whether we start with carbohydrate, i.e. glycogen and glucose, fats, these triglycerides, or proteins, they kind of follow fairly similar pathways. So we don't need to go bogged down into exactly how fats get there, exactly how proteins get there, as long as we've got an overview of that system. So for summary, it might be worth just pausing this and having a look over it. But the aerobic system is what we are using when we're at rest. It burns fat and carbohydrates. So as I'm sitting here, this terrible environment, I'm basically just burning sort of fat stores. A little bit of carbohydrate might be sort of feeding my brain, but not much else. If I was working exhaustively, the amount of carbohydrate I use begins to increase. And if I'm starting to work harder, the amount of carbohydrate I use begins to increase. But if I work exhaustively, my body might start using a little bit of protein. At rest, we burn mainly fats and a little carbohydrate. But as exercise intensity increases, we use more carbohydrate as fat takes a longer time to break down. So if the intensity increases further, we may need to supplement the energy with the anaerobic lactic acid system. It is less efficient, we use more fuel more quickly, and cause lactic acid to accumulate. We use our aerobic system to recover after short bursts of activity. So for a footballer, for example, requires a good aerobic system to support the distance jogged or run at low intensity during a game. But put simply, a well-functioning aerobic system will make most activities feel easier at any given intensity. A good aerobic system means that you'll use your lactic acid system later within exercise. So it means that it kind of supports your performance in football by kind of delaying the point at which you start to use those higher intensity energy systems and you create lactic acid as a byproduct. The aerobic system is also important because it's used to help our body recover and clear that lactic acid. So I've got some summary questions here. What are the three fuels used by the aerobic system? Which fuel is the primary source of fuel for exercise? So that reads badly. How many molecules of ATP are formed from a single molecule of glycogen that has been processed aerobically? And when intensity of running is gradually raised beyond the level that the aerobic system can cope with, which energy system supplements the aerobic system? And why might an athlete want to raise their lactate threshold, and how might it benefit their performance? So pause the presentation and just have a look at that. So I hope you've answered those previous questions. I've clicked off accidentally the wrong slide. So think about what we just said. The fuels we can use in our aerobic system are the fats, the proteins, and carbohydrates. When we exercise, the carbohydrate becomes much more of a dominant fuel. When we break down glucose to use aerobically, we kind of gain a couple of molecules of ATP at the start in glycolysis. We gain a couple more through the Krebs cycle. And then we gain loads more, an extra 28 at that electron transport chain. So our net gain is around 32 molecules of ATP. So you can see how much more efficient it is than if we were just using our lactic acid system where we gain 2. And why we might raise that lactate threshold, that point at which our body starts creating lactic acid, is simply that. If we can delay the point at which we can create lactic acid, we can just work at a much higher rate before we start experiencing fatigue. So on here, it says now fill in the relevant section of your workbooks that asks you to describe each of the remaining energy systems. And thank you, and goodbye from this hellish environment.